I guess this makes it clear why the confocal sensor is also a winner in the glass industry. My name is Lian, I'm a sensor specialist, and in today's video you will learn all about the thickness measurement of glass by using the high precision confocal technology. In the first step you will learn how the confocal technology works, what its advantages are and what it can be used for. Then I will show you the exact components of a sample setup, including the needed hardware and software, and we will also look at the integration possibilities. And in the last part of this video, we will configure a sample system and run some test measurements so that you get a better understanding of the capabilities of this system. And if any questions arise while you're watching this video or you want to know more about the confocal technology, then you will find the contact details in the video description below. Alright, so let's look at the confocal technology. A confocal system consists of three parts. The first one is the controller, which handles all the processing, the inputs and outputs, and it contains a white light source, which typically covers the full visible spectrum. This light is then funneled through a fiber optic cable to the sensor. The sensor contains multiple lenses which split up the white light into the various wavelengths. So the shorter wavelengths, like the bluish colors, are then closer to the sensor face, and the longer wavelengths, like the reddish colors, are further away. If we now place a target into the measuring range of our sensor, a specific wavelength will be reflected back with the highest intensity. So by building a correlation between the wavelength intensities and the distance from the sensor face, we get a high precision distance measurement system with resolutions in the nanometer range. Now you might think, what does the distance have to do with the thickness of glass? That's actually pretty simple, because we will get a reflection at the top side of the glass and one at the bottom side of the glass. And since these reflections are both converted into a distance signal, we can then calculate the thickness of the glass by subtracting the two measurements from another. And this brings me already to the biggest advantages of such a confocal system, because not only can we measure various transparent materials like glass, polymer films or similar, we can measure multiple layers of them, and we can do all of this contactless with a single sensor from a single side. So compared to other measurements, you can now measure all these details even with high space constraints. For example, when we look at a glass bottle and want to measure the thickness of it, then you don't need a second device which goes into the glass bottle, because you can measure everything from outside of the glass bottle. I guess this makes it clear why the confocal sensor is also a winner in the glass industry. And that's it about the theory. We can now move on to the practical stuff, and I'll put all the details of that into the video description again. As we discussed before, we first of all need a controller. Here we have a Micro-Epsilon IFC2422 dual channel controller, which allows for the simultaneous use of two sensors. And by the way, even if we would be talking about a single channel controller, multiple different sensors with different measuring ranges and shapes can be calibrated to such a controller. They can just not be used simultaneously then. So that's the controller. Then I have here the fiber optic cable, which I plug into the channel 1 connector, and on the other end I plug it into the sensor, which in this case is an IFS 2405-1 with a 1 mm measuring range. Note that there exist sensors which have the cable directly integrated. Additionally to that, I need a simple 24 volts DC power supply and also an Ethernet cable in case I want to use the Ethernet output, which I want to do in this example. But you have a lot of different integration possibilities. Aside from Ethernet, there are the digital interfaces EtherCAT and RS422. And with a separate interface, you could even integrate into Siemens PROFINET or Allen Bradley Ethernet IP. And just in case you'd rather like to evaluate analog signals, there is also 4 to 20 milliamps and 0 to 10 volts. That is the hardware part. If you want to use Ethernet output, then you have access to a free software which is called SensorTool. And with this software, we will now configure the system and do the test measurements. But before we do that, if you found this video helpful so far and want to see more stuff like that, subscribe to the channel and also to the Sensor newsletter. You will find the link for that in the video description. So when we start using SensorTool, we first of all select the sensor group, which in this case is the confocal DT. And for the sensor type, we select the controller. In this example, I'm using the IFC 2422, and now we're ready to search for the connected sensors. You will then see the confocal system in the results, and it might be the case that you have to configure the IP address for it to match your IP subnet. Once that is done, we click on Start Data Acquisition, and you will see that the software already gives you measurement outputs in case there is an object within your measuring range. But before we even start measuring, let's make sure that everything is set up correctly. For that, we go to the Settings tab and click on the button which will open up the web interface of the system. Then we again go to the Settings, and here we first of all make sure that the correct sensor is selected, because as I mentioned before, you can have multiple sensors calibrated to the controller. After selecting the sensor, we do a so-called dark reference. The dark reference simply eliminates noise signals that we get from the back reflections. Such back reflections always happen whenever there is a break in our optical chain. So, for example, at the connection between the fiber and the controller, and the connection between the fiber and the sensor. Here, a tiny amount of light will be reflected back to the controller, and in order to not interpret these reflections as distant signals, we have to run this dark reference. By the way, this of course only needs to be done if you reconnect some part in your optical chain. So for example, when you switch the sensor or the fiber. Now, before we click the button on this, we need to make sure that we either fully cover the sensor so that no light enters the sensor, or we make sure that there is no object within the measuring range that could potentially create a reflection, because we only want to adjust the system to remove reflection signals within the optical chain. But of course we don't want to remove reflection signals coming from a target. Therefore, I move the sensor away from the sample target until the software shows me that we are out of range, and now we can do the dark reference. This will take a few seconds, and then the adjustment is done. Aside from what we've done here, there are a lot of other settings, but these are not too relevant for our example here. The next thing we do is that we go to the Home tab, and where it says Measurement Configuration, we select the one-sided thickness measurement, so that the system not only evaluates a single reflection that we would get from an opaque material, but rather it now evaluates multiple reflections, which gives us the possibility to measure thickness. There is still one thing left for us to do. We go to the Settings tab again and then to Data Recording. Here we click on Material Selection, make sure that it's activated, and we need to select the material that we want to measure the thickness of. By selecting the material, we are basically telling the system which refractive index our material has, because depending on the refractive index, the light will be reflected back differently. This is just a physical phenomenon. You can look up Snell's law if you're interested in learning more about that. As a sample target, I have a tempered glass phone screen protection, and to be honest with you, I don't know the exact material of that. It could be a soda lime glass, which typically has a refractive index of roughly 1.46, and therefore I'm just gonna select fused silica here, since it has roughly the same refractive index. And with that, we can now start our measurement. I will lower the sensor towards the target material, and you can see that first the distance 1 is starting to show values, and when I get closer, distance 2 is also showing values. Once both distances of the first channel have values, the thickness is being calculated. And just keep in mind that the second channel of course won't give us any values, since no sensor is connected to the second channel. Alright, with this we have finished all the configurations, so we can press the escape key now to close the web interface and return back to the software, as you usually only use the web interface for changing the settings. Back in the software, I'm gonna disconnect from the sensor and then reconnect again. Then we go to measurements, and now in the bottom we can choose which signals we want to see, and we can also increase the number of digits. On the left there are all kinds of signal processing options, and I can even export the measured data as a CSV file. Another cool thing that I want to show you is the video signal. Remember when we said that at specific distances, specific wavelengths are being reflected back with the highest intensity. this is basically what we're seeing here. We have one reflection closer to the sensor and the bluish colors, and one reflection further away from the sensor into the direction of the reddish colors. And from both of these intensity peaks, we are now able to calculate the thickness. And that's it for this video. If you're interested in this technology, make sure to check out the video description, as you might be eligible for a free consultation. With that being said, I wish you a successful automation of your quality control process.